Yes, and he says it's not memorization, it's physics, even though it's still memorizing something about it.
All right, let's get the show on the road. Right, so hopefully we can get this thing done when we can. Everything, all the notes now are on the web. I might update some, try to get some things I'd like to improve. We'll see what we can do. But I just want to remind everyone that the final project is due on Monday. And that's really not going to have an extension because I'm going out of town. I'm going to Colombia, Mexico City, which would be very cool. And so anyway, I want to get this done for you. So anyway, hopefully. Okay, so today I want to talk about spontaneous emission. We've alluded to this sort of from the beginning, but we haven't actually solved. We've talked about how we need quantum field theory to explain spontaneous emission, but we haven't actually showed how that comes about. So, spontaneous emission, what we've been looking at in what we studied in the last week, we studied the Jaynes-Cummings model. Which is the model of a two-level atom interacting with one mode of the quantized electromagnetic field. And so, that was the story of a perfect infinite Q cavity with perfect mirrors. And if we started the atom in the excited state and we had no photons in the cavity, if we had the vacuum, then what we saw that the Jaynes-Cummings model predicted is that, well, we would dump one photon in the cavity, the atom would go to the ground state, and there would be one photon in whatever cavity mode was resonant with the cavity. And if this cavity mode was on resonance with the atom, we would just oscillate back and forth, and the probability to be in the excited state as a function of time was the sine squared of the coupling constant for one photon in the cavity. And we would have this kind of oscillatory behavior where the atom would go to the ground state, emit a photon, and then come back up.
If it starts out in the excited state, should that not be a sine squared?
Yes, this one would be cosine. Thank you. So this kind of oscillatory behavior is quite interesting. But this is not what we know to be the same phenomenology as spontaneous emission, right? If we started in free space and we started the atom in the excited state, say the first excited state, and there was no photons in the near the atom, near that frequency, it's the vacuum for all intents and purposes, then what we know is that the probability amplitude will decay, and we could say the states, if we started in the excited state at time t=0 at a later time, so the probability of being excited state at time t=0 is 1, then what do we expect the probability to be in excited state at a later time? Yeah.
Exponential decay.
Yep. So it will decay exponentially at some rate that we call the spontaneous emission rate. this is very different behavior than this. This behavior is reversible. So at any point, I can stay here, I know what the state is, and I can time reverse it and get back. And this oscillatory behavior goes on forever and is time reversible. So this model is oscillatory and reversible, time reversible. At any time that's because the time evolution is described by a unitary map. And this unitary operator is invertible. We can just write this U dagger. So you give me the state at any time, I could just multiply it by U dagger and I can get the initial state. Whereas this is a decaying exponential. It's not oscillatory. And moreover, let's say at time equals 0, I started in the superposition of the excited and ground state. Let's just suppose I were able to do that. Okay, I put on some kind of Rabi oscillation and I stopped. What would the state be as t goes to infinity? What would the state be? It would be in the ground state. And I would completely have lost any information about what the initial state is. There's no way to get from the state at the late time to the initial state. The information is gone. This is irreversible. Opposed to reversible. In fact, this dynamics that describes this is not unitary. This is not unitary evolution, which maybe you probably haven't studied in your quantum mechanics course. We always think about there's a Hamiltonian and then there's the time evolution operator. This evolution is in some sense more general, okay? So why, these are clearly two very different kinds of physical situations. I mean, we see that, all the time in classical physics, right? I mean, I can have an oscillatory motion or I can hopefully break that thing and then it's not putting itself back together, all of a sudden something kind of irreversible. Never mind. Someone will do that. Yeah.
They don't seem entirely counterfeit because in one case we're only considering the atom, but in the other case the state is also.
No, but you're absolutely right. So that is kind of the whole part of the whole story here. If I just look at the atom alone, in this case, I have this oscillatory behavior, but you make an important and excellent point. This system is what we call a closed quantum system because we have taken into account all the degrees of freedom, right? The degrees of freedom of interest here are the atomic degrees of freedom and the field degrees of freedom. And taken together, if we accounted for everything in the universe that involves, that's closed, and that time evolution is unitary. This system is what we call an open quantum system because there are other degrees of freedom that we're not accounting for, okay? So, but it's more than just that. It's also that the open degree of freedom is something like a DAF, meaning that there is a whole, not just one, this was just one mode of the field. It's a very simple situation. It's like two coupled oscillators, and they're gonna, I can start the motion of one oscillator and then I'll get to the other and they'll go back and forth. But if I had a whole continuum of oscillators, then the excitation in this one oscillator would spread to all the other oscillators and maybe never come back. In the same way, why did that thing shatter and not come in? Because, well, those vibrations went into the wall and went all over the place, and they just didn't reassemble the thing all together. So the story of open quantum systems is an important one we will focus on and talk a lot about next semester. This will be our first foray into that. Okay, so this kind of description can never be exact, right? Because the microscopic laws of physics are all time reversal invariant. In fact, I still think that's a very important fact. You know, the question of the arrow of time, why we, see time moving one direction. There's nothing in physics that tells us time should go in one direction or another. But effectively it does in the way that somehow entropy plays a role. So we're never going to get this exactly, and it's always a bit, seems like a lot of hand waving. So put your hoods on, because there's going to be some breezes here today in terms of trying to actually derive this from first principles, because it's an excellent approximation, but it's always an approximation, okay? And we'll come to see that in detail in just a little bit. Excellent. All right, so to do this, we're going to now, instead of thinking about the James Cummings model with a single mode, we're going to think about the ultimately continuum mode, the infinite number of modes that couple to the atom. Yeah, Tom.
Just a question about reversibility is.
Yeah.
Is not wave function collapse irreversible?
Oh, that's an interesting question. I mean, the relation. The answer is no. I mean, what we talk about as wave function collapse is based on, it's more like the following. I have a piece of chalk, it's a blue chalk. Okay? Which hand is it in? You don't know. You assign a probability distribution. Oh, maybe. Okay, try it.
So it's all hidden variables.
So the question is, where is that piece of chalk? Your probability distribution is 50-50, you don't know. Now you know, okay? So the wave function collapsed, you just collapsed the probability, the state of the system changed because you learned something new. Now, I don't want to get into the whole story of hidden variables, what's different about the wave function, but wave function collapse is really Bayesian updating, meaning I had a prior, I had some state assignment, I understood, and then later I learned something. This is different. This is more about loss of coherence. And the loss of coherence is coming from the coupling environment. So your state might become mixed. It can become mixed. The state of the system here is a pure state. It ended as a pure state. But intermediately, it's actually a mixed state because you don't know whether the photon was emitted or not. And so, depending upon whether the state is emitted or not, so what this corresponds to is I start on the north pole of the Bloch sphere, say an excited state, and I go through to the south pole. This is what's sometimes called an amplitude damping channel. In the middle, I'm a mixed state. So this is about the loss of information, not about the gaining of information. Information we've lost because it's went into the other degrees of freedom, and we don't have access to them. So this is just the facts of life, that most things that we try to manipulate and control are going to be noisy and damped because they're coupled to so much other crap that we don't have access to. So it's just impossible to really maintain this perfect oscillatory behavior because nothing is coherent forever. All right, so with that said, we're gonna solve this problem by looking at the problem of the two-level atom coupled to the quantum electromagnetic field. We've written down this Hamiltonian. We started with the, we could start with the fundamental quantum electrodynamics, but we simplified this by writing this as a two-level atom. So we have our two-level atom, which has an excited state and some ground state, and there's some energy. We'll take the ground state to be at zero energy, and the energy of the excited state is h bar times the Bohr frequency, okay? So that's the atomic Hamiltonian. Then we have all the modes of the electromagnetic field labeled by their wave number and polarization. And then we had the dipole interaction, which we wrote as h bar g for that mode, where we absorb a photon, annihilating it, and raise the atom, and then we have the complex or Emission conjugate. Okay, so this was our quantum optics QED Hamiltonian, which, as we remember, had a few approximations in it. One, we're talking about low energy, so we don't have any positrons or anything like that. Secondly, we did the multipole expansion, and the multipole expansion told us that the interaction coupling constant thus was the dipole matrix element, the matrix element of the dipole operator between those states dotted into the polarization vector times the mode amplitude, and we're going to take box quantization in a volume V. Okay. Now, this quantization volume at the moment, it's just a mathematical tool that allows us to write this to start as a sum, because we're putting boundary conditions. This is with periodic boundary conditions, as we discussed some weeks ago. And the quantization volume is just a way of us quantifying the number of modes. But ultimately, unlike this problem that Jane's coming out where there's a true cavity, there ain't no box. This is just a tool that ultimately we have to take the box, the boundaries out to infinity to be able to get something that gives us the physical picture, okay? So we made the dipole approximation, low energy approximation, and we made the rotating wave approximation. The rotating wave approximation and the other approximations that go along with it were about resonance. The fact that there is a resonance, that there is an energy level, means that if I started the population here or here, the dominant coupling of the field to the atom is on resonance. Everything else is a small effect. And so because there exists a resonance, and because we're starting the population in either one of the states where the resonance exists, is what justifies this as a good approximation. Okay? Yeah. All right, so now this Hamiltonian, because we've made the rotating wave approximation, still conserves excitation number, right? Meaning that if I have n excitations, those n excitations can be, I can subtract one of those excitations from I say I had n photons. I can absorb one of those photons and put in the atom in the excited state, and vice versa. I still couple, I can't change the total number of excitations. If I say the number of excitations is the number of photons plus the number in the excited state, okay? So in the case where my initial state is the atoms in the excited state, and I have the vacuum, okay? So we're talking just about spontaneous emission, not stimulated emission, okay? And this can be a great approximation, say at room temperature. You know, I don't have exactly, this is, you know, superbidium atoms, I don't have any 780 nanometer photons anywhere. So for all intents and purposes, it's the vacuum for the photons that matter, okay? So if this is my initial state, how many excitations do I have in the system? One. So the only basis states that contribute are the atom in the excited state with no photons, or the atom in the ground state with one photon, but in some mode, okay? And this is an infinite number of possible states, because the modes correspond to plane waves, which are propagating in some direction, which have some polarization on that. And there's an infinite number of different modes that contribute. The atom, in principle, could emit into any direction I want, okay? Yeah.
Practically all of those, oh wait.
They have
Wavelength is the same.
they're
No.
close. I mean,
They all have to be within.
they have to be close. It's not exactly the same magnitude of K. They have to be close to resonance to contribute. But importantly, there's all 4 pi steradians of directions, okay? So there's both a range of lengths, the wavelength or frequencies. Remember, the frequency here is C times the magnitude of K. This is a range. It's not exactly on resonance, so there's a continuum of frequencies that can contribute, and importantly, directions and 2 different polarization states.
4 pi steradian directions times 2.
Yeah, also known as infinity. Okay, so we have an infinite set, and this is important. This is why we only had 2 Hilbert space vectors that were coupled. We would have oscillatory behavior. The fact that there's an infinite number of these is why we will be able to ultimately get behavior that's not oscillatory, that is well approximated as something that looks like exponential decay. We shall see. Yeah.
With infinite numbers, because we can have infinite number of pairs that are always just one apart.
Say again, I didn't quite
We have
get that.
infinite pairs that are one excitation of, or that have.
No, this guy
excitation.
couples to all, not just pairs, it couples to all of them. Let's write down the equations of motion, okay? So now I just want to write down the Schrodinger equation. So what this says is that the state at a later time is a superposition of these basis states. These are the only basis states that contribute. So I have some amplitude in the excited state with no photons, and then the sum of all the modes, which is an infinite sum, the probability amplitude to be in the ground state with 1 photon in that mode, and the atom in the ground state with 1 photon in the mode. Okay? So this is the general state vector at all times, okay? With the initial condition that at time t equals 0, I have that amplitude is 1, and all the other amplitudes at time t equals 0 are 0. So that's my initial condition, and I want to solve for, ultimately what I'm interested in, I want to solve for the probability amplitude in the excited state as a function of time. So I'm going to solve the Schrodinger equation. The Schrodinger equation says that the time derivative of this is minus I over h bar, the Hamiltonian, times that. Okay? And this is my Hamiltonian, and I can solve it. Now, this problem is similar in spirit to one that, you know, if you've taken 522, also known as quantum 2, this is the problem of time-dependent perturbation theory, in the sense this is a weak perturbation compared to the, so when we're doing time-dependent perturbation theory, it's convenient to go to the interaction picture, okay? So we're gonna go to the interaction picture first. We can go to any picture we like, it's very convenient to do that when we have this kind of weak dipole coupling compared to the strength of the, it's just basically when h bar g is much, much smaller than this or, any of the other energies in the system, okay? So this is the approximation one of the approximations that's important. And when we do that, it's useful to go to the interaction picture. The interaction picture is one in which the interaction Hamiltonian in the interaction picture is the Schrödinger picture Hamiltonian, but with the free evolution in it, okay? So this is in the interaction picture. This is my interaction Hamiltonian, and this is my free Hamiltonian without the interaction, which we're calling H0, okay? So in the interaction picture, A and sigma plus and A dagger and sigma minus evolve according to the free evolution without any coupling. And so that gives us the following form. This guy goes like e to the minus I, e to the minus I, omega k minus omega e g t, plus the Hermitian conjugate. Okay. So that's the interaction Hamiltonian in the interaction picture. Okay. It's time dependent. In the interaction picture, the state evolves according to the interaction Hamiltonian in the interaction picture. Okay, so everything is in the interaction picture. All my amplitudes are in the interaction picture.
What's I?
I stands for interaction picture.
I see, sorry.
That's the superscript is to say this is all in that picture.
If I stands for interaction, why is in?
There's the interaction picture and there's the interaction Hamiltonian, okay? So this is the interaction Hamiltonian in the Schrödinger picture. If I was pedantic, which I am, I could write a superscript S on that to say it's the interaction picture. I could write any operator in the Heisenberg picture or in the Schrödinger picture, in the interaction picture. This is the interaction Hamiltonian in the interaction picture.
Which is presumably going to be simpler than before.
Yeah, it's because we see the resonances already appearing. It's going to be important. Okay, so now what I want are equations of motion for the amplitudes, right? So this tells me that the time rate of change of that amplitude, I take the matrix element with E0, that's what that amplitude is, which is equal to minus I over H bar So when I do that, what I see is the only term that contributes, where's the interaction picture Hamiltonian? Oh, here it is the thing that if I plug in the state over there, then I see that the terms that take me from the ground state to the excited state. So this is going to be minus I over H bar in the H bar, sum over K and mu, G, K, mu, over there, where is it? Oh, here it is. And this guy raises, so it couples the thing with one photon, so it couples G with one photon. Okay. So the amplitude in the excited state is coupled to the amplitude in the ground state by the absorption of a photon that was in that mode, okay? And I can solve for, similarly, this guy, which is going to be the other term here with the conjugate. So it's going to have minus I G1 or GK mu star G E 0 of T. Let me make sure I got that right. Oh, I forgot these factors. I didn't get it right. So this guy has a e to the minus I omega k minus omega e gt. And this guy has an e to the plus I omega k minus omega e gt. So these equations of motion are similar to what we saw for the Jaynes-Cummings model. The only difference being is that I don't have a single mode. I have all the modes, and so this is an infinite set of coupled ODEs. Okay, so this guy is coupled to all the different modes, and so forth. Yeah, man.
You already answered this question earlier. I was just gonna say like, oh, this is just of the frequency that are near resonance, right? You already said that.
Yeah.
I'm not sure if I quite understand the interaction picture. Like, it's like you're doing the Heisenberg evolution of the, like, why don't you do the Heisenberg evolution of the full Hamiltonian? Like, why does this give you an accurate description?
Any description, I can make any unitary transformation I want. I can put any part, I have multiple terms in a Hamiltonian. I can put any part of it into the state and any part in the operator. In the Schrodinger picture, I put it all in the state, none in the operator. In the Heisenberg picture, I put it all in the operator and none in the state. The interaction picture says, I'm going to put just the free evolution into only the free evolution into the operators and keep the interaction part in the state. It's because when it's a nice way of doing perturbation. When you're doing time-dependent perturbation theories, when this is a small term, it's a way of keeping those terms. So if you've done the usual Dyson expansion, it comes from doing the interaction picture. So when we have a weak interaction and we're doing time-dependent perturbation, it makes the approximations go easier. It's any picture works. I can put any part of the time evolution to any part of the state of the operator. Is up to us. All right, so we have this coupled set of ODEs. We can't solve them exactly because it's an infinite matrix, okay? But, so now we're going to do a series of approximations. The first thing we can do is we can just integrate this differential equation formally, given the initial condition that we have nothing in here. Then the solution to this differential equation is that the amplitude in the ground state with one photon in that mode at a later time is minus I G K mu star. The integral from 0 to t et prime e to the I omega k minus e g t prime. That's just the formal integral of this. If I take the derivative of this, I get that. Okay? I didn't really solve anything, I just integrated the equation. But now I can substitute this back into the equation of motion for the excited state and get what's called an integral differential equation. So I'm just going to take this formal solution and plug it back in here. And what I get is minus the sum over all the modes, the magnitude of that coupling constant squared, and then I have the integral, I'll put the integral out front. And then I have this with this, which is either the minus I omega sub k minus omega eg t minus t prime times the amplitude of the excited state. So all I did here is I took that solution and I plugged it back into this. Now, all right, but that's no solution because this appears on both sides. I mean, my goal is to solve for this thing, but I can't because this is inside the integral, okay? This is in what's called an integral differential equation. But I just want to kind of point out this whole thing over here is some function I'll call k of t minus t prime, okay? I can call it the kernel, if I like, okay? Now, the whole story here is the nature of this kernel. What we would like to be true is that, or get to the point where this thing, or this. Because what's the solution to that differential equation? If this were the equation of motion, then the solution is probability is the square of it, we go like this. In fact, we could, if we wanted to, add in an I delta. It wouldn't change anything. It would still, in fact, we're going to see that that would still be the probability to be in the excited state with no photons would be decay exponentially. There you go, I would square it. It's the square of the sample. So if that were the solution, we'd be done. In fact, it is the solution. We want to get to that point, okay? At least it's approximately. So what would that say about this thing? It would say that the rate at which this thing changes at a given time only depends on the amplitude at the same time, and not its whole history from 0 up to that time. Let me just finish this thing. Okay. Now, this is the exact thing based on the Hamiltonian. Why does this amplitude, how it's changing in time, not just depend on its value at that time, but it depends on the whole history from 0 to t. Yeah, maybe.
Because the paths can interfere if there's a quantumness.
Well, it's not really about quantumness. It's about the fact that this is an open system. I mean, it came from here. Because really, what the excited state's amplitude depends on what the ground state is doing. the ground state is what the local amplitude of the ground state at time t affects how this, because they're coupled through that off diagonal. I get your question in just a moment. I just want to finish this thought. But by, so the whole history is here. What the ground state here depended also on the ground state expected the excited state. So that generally means if we're only looking at one part of the system and not the other, I generally don't have local on time. It depends on the whole history. By turning this into something that looks like gamma over 2 times a delta function, or at least the real part of that, if that were the case, then if this were done, I get back this. So the degree to which this is local in time is the degree to which this is true. And that's what's known as the Markov approximation, which we'll talk about a lot more next semester, but this is just a prelude into that. It's basically saying that there's information to make this thing irreversible. At this point now, it's become irreversible. Because I turned what was a whole history, which had all this information, and I kind of threw it away. I said it didn't matter. That information was not accessible to me, and I turned this into a delta function in time. We'll have to understand where that comes from. Once we do that, this is where the thing becomes irreversible. Because I've lost the history. I don't know where I came from anymore. And that's going to be the whole story. Yes, Donald, so questions?
You might have, I think, just answered it, but I was going to ask, it seemed like in our derivation we were going from, we want this, which means that this has to be that. But you just, I think, gave some background when it would make sense for it to actually be.
Yeah, so right now, I'm trying to just give a little bit of a, sort of foreshadowing of where we're headed. This equation of motion can be something that looks like exponential decay if, for some reason or another, we can take this kernel, which is a finite correlation time, let's say a time in which what happened in the past affects what happens now. If I lose that, and I lose that correlation time, which is in some sense how long this thing, the past affects the present, not just the present affects the present, is what's known as the Markov approximation, which we're going to have to see under what that approximation is.
So can you say that for a process which has spontaneous emission, like the environment is Markovian?
Absolutely. 100% Markovian, as we will see. The most perfect Markovian approximation you will ever have in the universe. Okay? And we'll get to that in a moment. Because as we're going to see, the question is, what is the time scale over which this thing has memory? And now it's got no memory. T and T prime doesn't make a difference. What happens? Yeah.
This might be a wrong way to think about it, but by Heisenberg uncertainty principle, you can't know both position and momentum. So if you know exactly where you end up and how long it takes, you shouldn't also know the history or the momentum.
I don't think that explains this phenomenon. There is the question of the uncertainty principle, and we're going to see some notion of Fourier duality come in here in a moment. But really, this exact same thing is true classically as well. When I, threw the chalk against the wall and shattered it, there's a time at which the vibrations in the wall and in the carpet are correlated to the chalk, but at some point those correlations are lost. And then it's, I could just think about it as friction. So these stories are not unique to quantum mechanics. They're really about the idea of a small number of degrees of freedom, like something in the center of mass of this chalk, compared to an Avogadro's number of degrees of freedom and getting lost in 10 to the 23rd degrees of freedom. That's what it's really about. Good. All right, so let's get to it. So the first thing we want to do is, as I said, we have box quantization with periodic boundary conditions, okay? And I want to turn the sum into an integral over not only an infinite number of modes, but an uncountably infinite number of modes, because I really don't have no box. I just put it there to do the counting. And so the way we do this is the following. I think about K-space. Okay, so I have Kx, Ky, Kz are the three components of the K vector. Now, what we have when we did box quantization is that we quantized or discretized and there's, I'm not going to draw all of them. There's dots, discrete dots, which correspond to the allowed K vectors that were allowed by the periodic boundary conditions. So what we did is that we had a box with length Lx, width Ly, and height Lz. The volume is the product of these. And we put periodic boundary conditions. We may or we may not remember that we did that at one point. And then we said that the Kx values were some, number times 2 pi over Lx, and similarly for y and z. Okay? So those are the points that are allowed for a given box. Okay? Which means that we have a way of doing our sum and turning it into an integral. So what this means is that I'm going to take my sum over the modes and turn it into an integral over three-dimensional K-space weighted by the density of states. This counts, if I integrate this over a certain volume in K-space, this tells me the number of modes in that volume in phase space. Hold on a second, I'll finish this and I'll get to you. It's equivalent to the following thing. Suppose I wanted to count the number of air molecules in this volume. Well, I could count them, but for all intents and purposes, I could say there's a continuum with a density of mass, and I would just integrate that. So if I knew the density of mass and I integrated it over the volume, I get the total mass, and that's tell me how many air molecules. So this is a trick of counting modes by seeing what the density is of modes and then integrating over that volume to get the number of modes. Yes, now take your question.
We could think of a discrete case of just being that integral, but with the density of states just being a bunch of delta functions.
That's right. And then now we're just coarse graining. Okay? So what is the density of modes? Well, I have, I can just ask, in a volume of here, I have one mode inside this volume of, there's one mode, there's, 1/8 of them on each corner in that volume. So the density of states as a function of K space is 1 divided by the volume in K space, which is 2 pi Lx times 2 pi Ly times 2 pi Lz. This is the volume in K space, this volume, and I have one mode in there. They're shared, if you look at them, there's 1/8 of them on each of them, they share. So the density of states is the quantization volume divided by 2 pi to the 3rd power. Okay, so we're going to replace the sum over K by a integral over three-dimensional K space weighted by the density of states. So my rate of change of this guy is equal to minus the integral from, well, I'll put this guy on the outside now. The sum becomes an integral over K space, the density of states. The sum over the polarizations is still there. My G, the function of mu, function of K squared. And then I have e to the minus I omega K minus omega EG T minus T prime, the amplitude at time T prime. Okay? All right, so we need to actually now think about how we're going to do these integrals and sums. Yeah?
Would it still be omega subscript k or omega as a function of k?
Yeah, it's a function of K, but I'm just being lazy.
Do you still need the integral over t prime?
I do. I need that integral. Absolutely need that. Thank you, Leroy. Absolutely need that. All right. So now things just get a little bit, I have to think about K space. And I drew this picture somewhere or other of my plane wave modes that, there they are, right? And I need to integrate over this. So the first thing I'm going to do is decide what's going to be the polar axis. So it is easier to think about this guy as an integral in spherical coordinates, shells, rather than Cartesian coordinates. So that's k squared dk d omega sub k. That's my three-dimensional integral in K space. Okay, that's the solid angles in K. And I need to think about what my polar axis here. So here's K space again. And I'm going to define, there's only one direction that's defined in this whole problem, and that's the direction of the dipole moment. It's the only vector direction we've got. So we might as well call that the z-axis. So this is going to be the direction of the dipole. And then I have k in some direction relative to that. It has there's a solid angle associated with that. And then for every one of those modes, I have two polarization states. Okay? So let's think about this object, G mu as a function of K, was the dipole matrix element, H bar times that, was the dipole matrix element dotted into the polarization vector times the square root of 2 pi H bar omega sub K over V. Right, that was that. So we have to think about that, and we're going to have to do this integral. Firstly, if I take my two polarization states as the linear polarizations as I've drawn them, one of them is in the plane. I'm going to choose one of them in the plane that contains both K and D, and the other one perpendicular to the plane. That's a perfectly good basis of polarizations. The one that's perpendicular to the plane has zero dot product with D. The only one that has a dot product is the one in the plane. And if this is the polar angle theta sub K, then this dot product is equal to the sine of the angle times the magnitude of that. Okay? You can see that I just delimit when it's 90 degrees, they're parallel, and when theta is 0.
So now that we're working with infinite size, right?
Yeah.
What about that V in our Z?
Well, V, we're going to ultimately take, the V better ultimately go away. It can't depend on V. And we're going to see it's going to cancel.
Okay. It'll go away naturally.
It will naturally go away, but you're absolutely right to be concerned about that. in the same way that when we count the number of molecules, the way that volume goes away. All right, so very good. Remember, omega sub k only depends on the magnitude of k and not its direction. The direction only appeared here through the polarization that's different for different directions, okay? So now I want to think about this integral. The part of the integral I can do when I do this thing, I'm going to do a little aside and look at the integral over all directions in space of this sum. Okay, let's do that part of the integral, because that's the only thing that depends on the direction of the mode. The only thing that depended on the direction of mode was the way in which the dipole was coupled to the mode. So that's the only thing that appears in. And so that's equal to the magnitude of the dipole matrix element squared divided by h bar squared times the integral over the solid angle of the sine squared of the angle. Okay, that actually is the dipole radiation pattern. It's telling me that I can't couple to the mode that is radiating along it. I only radiate more perpendicular and I have the dipole radiation pattern. So that's where that's sort of appearing over here. This integral, you can do it, you turn it into sines and cosines, and this whole thing is 8 pi over 3. Okay? I'm not going to bother doing the integral. Okay, so let's put some of this stuff together. Of course, I used the wrong board. Right, so I'm going to call, let's see, do. Right. Oh, I missed this guy. So this thing is this times 2 pi h bar omega over v. So this whole thing is equal to 16 pi squared omega sub k divided by 3 h bar volume times the magnitude of the dipole matrix element squared. And then define that as the average value over the average of g squared as a function of omega. Okay. Let's leave that up over there and come back to this board. All right, so what I got is the time derivative of this amplitude is equal to minus the integral from 0 to infinity k squared dk times the density of states times this thing I call g bar squared as a function of omega sub k times the integral from 0 to t dt prime e to the minus I omega k minus omega ag t minus d times this. Yeah.
Should that be 2 infinity, not to k?
I'm sorry, this should be infinity. Yes. Okay. Finally, this thing we said only depended on, it's as a constant, it depends on the volume. And this thing I'm going to rewrite as omega squared over c squared d omega k over c. so that we're integrating over frequencies, okay? So this whole thing together, I'm gonna call d omega sub k the density of states in frequency space. So the point here is that when we integrate it over all the directions, what we're looking at is the number of states in a shell in K space of a certain width. And this width depends on the length of the K vector, which is another way of saying the frequency, because the length of the covector is just the frequency. So I can think about this as density of modes in frequency space. Okay, so let's, okay, good. So now I have this integral, and okay, so at this point, I really haven't made any approximations at all, other than the initial rotating wave approximation, the Hamiltonian, but every integral I didn't do anything. I just turned the thing into a density of states, and it's all fine.
Well, with the Markov approximation.
I haven't made it yet. I haven't made the Markov approximation. See, I've got t minus, there's no delta functions here yet. Here they come. Here it is. So now we have to look at this integral and we say, okay, I mean, this thing, you know, is proportional. Let's see, what is this thing? That thing is something proportional to omega sub k, right? That thing over there. So we got an omega cubed thing going on over here. Okay. There is, and this is where the whole story comes in. So this is equal to the integral from 0 to infinity, this thing, the density of states, times this guy, I'm going to bring this outside the integral here, omega sub k as a function. Let's write it this way. Just rearrange some things here, just to get a picture of this, okay? This object here is in some sense the spectrum of the bath. What is the bath? The bath here is the vacuum fluctuations, right? The atom is bathed in the vacuum. And the way in which the vacuum couples to the atom depends on the coupling constant here and the density of modes that tells me how many modes there are, right? To the degree to which if this spectrum were flat, if this spectrum was broad and had no spectral function at all, it was a completely flat bath, then what would this integral be? If this wasn't here, it would be a delta function. Well, if this went to minus infinity, but that's a detail. But it would be a delta function. What this thing is something that has it's not a delta function, but it's got some width to it, t minus t prime, that goes like 1 over sort of the width of the bath. If the bath, this spectrum, was infinitely broad, then this thing would be a delta function in time. Yeah,
The difference of, oh, you said in time.
I mean t minus t prime. What I'm trying to say here is that here's my kernel function, the one I was looking at before. The question of the time at which this memory exists depends on, in some sense, the spectrum of the bath. If the bath is infinitely broad, then we call it white noise. It has nothing, and then there's no correlation in time. If it's a spectrum of color, then it will have finite correlation time. That's what we would call non-Markovian bath, if there is any spectral features, okay? So what we're seeing here, the Markov approximation, is really about how broad this bath is, and therefore what this correlation time is compared to the other time scales in the problem. So the problem of the Markov approximation is a problem of multiple time scales. What are the two time scales? There's one time scale which I'm going to call the correlation time. The correlation time is how much time is the system correlated with the bath, and at what time do we lose those correlations? That correlation time goes like 1 over the bandwidth of the bath, the width of the bath's spectrum. If the spectrum has an infinite bandwidth, the correlation time goes to 0. It's not infinite, but it's damn big because it's just growing like omega cubed. There's another time scale here, which is the time scale over which the atom decays. Change of atom state time scale. How fast does the atom change? In this case, how fast does it decay? And if these time scales are way, way different, I'm going to look at my dynamics at a time which is infinitely large compared to the correlation time, but infinitely small compared to this. This separation of time scales is the story. It's the fact that there's a very rapid decorrelation, but it's such a weak coupling that it takes forever for it to decay. And because I can separate these time scales, I can take certain things to infinity relative to some things, and some things to 0 with respect to others. If you've ever, this calculation is equivalent to the derivation of Fermi's golden rule. If you've ever seen that, it seems crazy. In Fermi's golden rule, you're saying this is a time-dependent perturbation theory. It's a very small time, the atom or nothing will barely change, but then you take some other times to infinity, because you make this sinc function become a delta function. It's this. It's infinity compared to that, but 0 compared to this. This is just saying this is a weak perturbation. So we can look at not much has happened, but infinite path. Yes?
Are you able to sort of correlate?
What does this mean?
Are you able to describe physically what, having these two being different means?
Yes.
Okay.
So let's ask ourselves, in our problem, what is the bath? The bath is the electromagnetic vacuum. What is the time scale over which the dynamics in the electromagnetic waves are correlated to the atom, after which they're gone.
Like how long before the bath decays?
Well, it's not the bath, it's how long I can get information back. So there's the vacuum fluctuations are coming in, they talk to the atom, and then they go away. And they're going back. Well, there is a correlation time, but what's physically happening? Yeah, it's how long the light passes over the atom, after which that wave packet's gone, and the new wave packet, it's not coming back. If there was a cavity mirror, it could bounce back and hit it, but the time at which the vacuum fluctuations are correlated to the atom is the time it takes light to pass over the atom.
So wave packet length over C?
Yeah, it's just it's a Bohr magnet, not a Bohr magnet, the Bohr radius over C. That time is tiny, it's an attosecond. Compared to the time scale, that one little wave packet passing by the atom did almost nothing to the atom. It takes many, many of them before it's going to actually cause it to decay. And that is the time scale of the decay. So the time scale of decay, say, is, what's the lifetime of a cesium atom? 5 nanoseconds, right? Say sure. Yeah, it's about right. It's a few nanoseconds. Whereas this is, 10 to the minus 15 seconds. So there's a huge separation of the time scales. So there's a time at which the bath is correlated to the atom, by which the information's gone, it's not coming back, versus how much did it actually change the system. And since it's a weak interaction, the dipole coupling is small compared to the binding energy, the atom's population doesn't change very much. And that's where we'll finish this up. I don't want to take time at this point at the end of this lecture. We're going to take this to sort of see the degree to which at the end of the day we can do the Markov approximation is effectively this. The degree to which this is a delta function is the degree to which we can say, oh, it actually doesn't matter what this limit of this integral is, because this is only non-zero when t equals t prime. So it doesn't matter what this limit of the integral is, and we're going to get rid of that limit and take that limit to infinity. Okay. So we'll finish this calculation after the holiday, and we'll see from that how we can derive the formula for gamma, what the spontaneous emission rate is.
Class on Thursday?
We can Zoom over Thanksgiving.
Oh,
if you
it's
like.
Thanksgiving?
Yeah. People were about to kill you. All right. Have a wonderful holiday. We'll see you then.
Physics.
Yeah.